welcome Ron. Yes. So we are very happy to welcome Ron. He's nowadays at the Weizmann Institute in Israel. But before then, he did a PhD with a famous group in Tel Aviv. So Tel Aviv University with that I know Alex Lieberson, and they are among the 3 or 4 teams in the world able to perform nice Lagrangian experiments, etc. And during his PhD that Ron defended in 2019, he did some Lagrangian measurements in the wind tunnel in the presence of a canopy. So that was kind of new, and they were able to access many quantities. I guess, Ron, this is what you will be talking about.
Yes.
And yes, so Ron, the floors, we are very happy, and the floor is yours.
Thank you very much for the introduction, Laurent. And thank you all for coming. I'm very honored to give a talk for the ENS de Lyon team, which I've heard and read a lot of your work. As Laurent said, I'm Ron Schnapp. I did my PhD with Alex Lieberson, and I will be talking about my PhD research that was conducted in collaboration with Eyal Fatal and Yardena Borbotoviv from the Israeli Institute of Biological Research. Okay, so the topic of my talk will be on Lagrangian intermittency in canopy flows. So let's first try to understand what are canopy flows. So if we have the Earth's surface right here, and we have the air above it in the atmosphere, so the air is flowing in some direction, and then somewhat close to the ground, we have what is called the atmospheric boundary layer. And then in the very bottom part of the atmospheric boundary layer, we have the canopy flows. And this is actually the region where the air in the atmosphere directly interacts with the objects on the surface. So we have, for example, buildings, and we have trees, etc. And due to this direct interaction, we have quite a complex flow situation. So above the canopy, we usually have some kind of a shear instability, similar to the Kelvin-Helmholtz instability that generates these kind of coherent structures, which are very large scale and very important for the dynamics of what's going on here. And in addition to that, we have small scale of turbulence with apparently completely different dynamics than what happens outside. And this different dynamics occurs inside of the canopy due to the wake of the obstacles themselves. And of course, these two kinds of dynamics of the flow can interact with each other, etc., etc. So this basically leads to a very complex structure of the flow with a very strong turbulence as well. And we, of course, all know that because we all live in a turbulent environment. In the forest around us, the field or the city that we can feel the turbulence as we go in our streets or go on in our everyday lives. So indeed, this is the canopy flows and the turbulence that occurs in canopy flows is very important for many natural processes or not natural processes that occur all around us. So for example, canopy turbulence determines the air quality in urban regions because it basically ventilates the streets where we live at. It also determines the rate of exchange of moisture, CO2, other chemical compounds between the ground and the atmosphere itself. So for example, it's important for plant transpiration, etc. And it's also very important for transport of material inside, near the ground. So for example, pollen transport is caused by canopy flows. And also transport and dispersion of viral particles, as we've learned in the latest pandemic that we've had. So basically, the big question that people want to answer is, how can we estimate dispersion in canopy flows? So for example, if I'm standing right here near to my building, and I have in my hand some dust or smoke or whatever, and I just throw it into the air, then obviously it's going to disperse eventually in the environment, in the air around me. And we want to be able to model this dispersion or this growth of the size of the population of what I throw into the air very accurately. So basically we're asking, how can we estimate dispersion in canopy flows? So people have been trying to answer this question for quite a long time. And one of the common ways to do that is to use what's called the Eulerian framework, in which basically the flow is sampled at fixed positions in space. So for example, people use these towers, they put them inside a forest or maybe inside of a city, and they sample the air velocity as a function of time. People can do it also in wind tunnels. So if you have a big wind tunnel, you put your models of buildings inside of it, and then you put a static probe that measures the fluid velocity as a function of time. You measure this kind of signals, or you can have kind of optical methods that allow us to sample the fluid velocity on many different positions inside of the flow field, using, for example, the PIV method, as can be seen here. So this gives us really high details of the velocity structure around these kind of elements inside of wind tunnels. But in our study, we want to try and suggest a different approach to the Eulerian framework. And this approach uses the so-called Lagrangian description. So in the Lagrangian framework, we're imagining that the fluid, that the air around us is made up of small air particles, and that they move in time due to the velocity of the fluid itself. And then we prescribe the properties of the flow of the fluid on the positions of these moving trajectories, on the positions of these, the trajectory of these moving particles. And we track them as a function of time. And then we know, we have more information about the turbulent flows that we are in. And I mean, I guess this is quite a natural approach to study dispersion problems, because we're actually tracking what we are releasing inside of the flow. The problem is that we actually want to model the motion of the particles inside of the canopy flows. And this means that we need to have a firm understanding of the physics that goes on behind the building of these trajectories of these fluid particles. And although experiments that studied Lagrangian turbulence do exist, and they're are becoming more and more frequently appeared in the literature, when we look at the case of a canopy flows, there hardly exists any experimental data at all. So if we want to build a physically based model for dispersion in the Lagrangian framework that will be suitable for canopy flows, we don't have any data to rely on. And this is what we're trying to address in our big research. So as for this talk, we said that we need the physics behind the trajectories. So let's focus a little bit about the physics. As we said, canopy flows are very turbulent, very strongly turbulent. So we have to eventually talk about the basic phenomenology of turbulence. And this phenomenology is usually called the turbulent cascade. So basically, if we have some fluid, some flow, we can disturb this fluid by, for example, mechanically making it move with some tool. It can happen also naturally, just by some fluid instability at large scales, etc. And then these two actions can insert energy into the fluid and cause some motion at this large scale of the flow called L. However, due to natural fluid instabilities, these motions at the scale L usually are unstable, and they will be broken up into smaller scales. So for example, this guy was broken into 4 different what we call eddies, and then these are again unstable, so they are broken up into smaller scales, and then these are broken into even smaller scales, etc., etc. Where the kinetic energy that we have injected here at the largest scale is being preserved along all of these steps of the cascade. However, eventually, if we have the scales right here at the bottom that are at the smallest scale of the cascade, the energy eventually cannot be transmitted into smaller scales, and the energy is being dissipated due to friction. So this is the basic phenomenology of turbulence. And this eventually leads to a scaling law for the velocity. So if the characteristic velocity at this scale, we denote it as VL, then the characteristic velocity that we have for these smaller scales that we denote VR will be proportional to VL times some the fraction of the scale that we are at to the largest scale of the flow with some scaling exponent h. So essentially, the fundamental phenomenology of turbulence is a self-similar picture, where every time that we look into a smaller step of the cascade, we see basically the same picture as we have seen above, but just scaled down by the scale, and the velocity scale. The scale of the velocity is scaled down as well. And the nice thing is that we have very nice models that can recover such self-similarity. So for example, we have the model that was proposed by Thomson in the 1987. However, is this picture, let's say, 100% accurate? And unfortunately, it's not perfectly accurate. If we want to go into the next step, we have to consider the new phenomena, or not new phenomena, another phenomena that's called intermittency. So basically in 1949, Batchelor and Townsend performed a very famous experiment in which they saw that turbulence, at least at small scales, is very highly active, but only during small fractions of time and in small regions of space. So for example, Shea Jackson and Orsag in 1990 published this very famous picture from their DNS simulation in which a turbulent flow was simulated. And then we can see that there's a lot of vorticity and a lot of kinetic energy that is concentrated into these what we call vortex filaments. And essentially, this means that the accuracy of the self-similar cascade picture is not 100% precise. So if we want to be more accurate, we want to be able to take into account this intermittency phenomena. So the big question that we will focus on today, that I will focus in my talk today, is how do these two separate objects, how do they interact? Can they exist together? So in particular, can this kind of cascade of turbulent energy maybe adjusted for this phenomena of intermittency? Can all of this exist in a canopy flow that is highly inhomogeneous and very complex to understand and to describe? Okay. So in order to answer these questions, we have performed an experiment. Basically, we went to the Israeli Institute of Biological Research, and we took their environmental wind tunnel that is seen right here. This is a very big wind tunnel. It is 14 meters long, and it has, this is just the test section, and it is 14 meters long. It has a cross section of 2 meter by 2 meter. So it's a fairly large wind tunnel, actually the largest in Israel for these purposes. And it is suitable for performing experiments that try to mimic the atmospheric boundary layer. And then in order to simulate a canopy flow, we just took flat plates and we laid them all across the bottom part of this test section. So these are the small plates that we have. This is a kind of CAD model for these small plates. They have heights of either 100 or 50 millimeters. And then we turned on the wind tunnel, meaning that we blew air above these flat plates, velocities of either 2.5 or 4 meters per second, which gave us a canopy flow with a Reynolds number for as for the plates of around 20,000, meaning that we have quite a high Reynolds number, which generated quite a strong turbulent flow. And then in order to gather statistics in the Lagrangian framework, we used what is called the 3D PTV method. So in 3D PTV, we are taking a bunch of cameras. In our case, we took just 4 cameras. We put them outside of the wind tunnel, and we activate them. We ask them to record what they see at a very high rate, so either 500 hertz or 1000 hertz. And then we go inside the wind tunnel and we throw a lot of dust into the air. This dust has to be very small in order to ensure that it faithfully tracks the flow. And then we used a very strong laser in order to illuminate these dust particles that we call tracer particles, as we can see here. And then we took their images during our experiments. Since we have the 4 different cameras, we can triangulate the position of these tracer particles as they flow inside the wind tunnel and obtain their 3-dimensional position. And then since we are taking the images quite fast, we can actually track their position as a function of time and construct such trajectories. So conceptualized, it would seem like something like that. And then if we just continue and record the data for very long times, so for example, we recorded roughly 6 hours worth of data, then we can reconstruct millions of such trajectories that will allow us to gather statistics on the turbulent flow that we have inside of the wind tunnel or of the canopy flow itself. So just to see roughly how it looks, I'll just go here and show you this animation that I made. So this animation kind of shows the trajectories flowing inside of the wind tunnel. This is real experimental data after processing, of course. We have here the roughness element in the flat plate inside of the wind tunnel. And we have this blue arrow that points in the direction of the wind. And then we can see these pink kind of pasta tubes that represent the trajectories moving inside of the canopy flow. So this is how it looks. And this is the data that we are trying to analyze that we will consider in this talk. Okay. So let me go back here.
Question in the meantime.
Okay.
On your animation, so, yeah.
Yes.
On your animation, we see the the fluid particles really close to the little thing that you put, the 50 millimeters blades or something.
Yes.
Do you actually
Yes.
need the 2 meters high wind tunnel? Is there an influence of the fluid above?
Yeah, so the entire dynamics inside of the canopy flow is being forced by the air inside of the boundary layer. And as I said, in the boundary layer above the plates, we have a very complex structure of kind of coherent structures, etc., that influence very strongly the dynamics inside of the right, in the region between these canopy obstacles. So we think it was very necessary to have a well-developed boundary layer above these obstacles in order to really consider that as a canopy flow. I hope this answered the question.
Yeah, thank you.
Sure. Okay, so just a first glimpse. As I said, the canopy flow is extremely inhomogeneous. It's non-ideal, it's anisotropic, and this can be seen in this scatter plot. So here I just plot a scatter of the two velocity components, the streamwise velocity component and the vertical velocity component as a function of height. So what we have here is a scatter plot for the velocity deep inside of the canopy, right, really low between these obstacles. But this is much higher above these canopy obstacles. And we can, I mean, just visually looking at the scatter plots, it's clear that the statistics change quite dramatically with height, right? So the intensity of the fluctuations of the turbulence are lower inside of the canopy and much higher outside, and also very strongly anisotropic. So as we go higher above the canopy, we can start to actually see these kind of coherent structures that really cause very strong anisotropy and asymmetry for the distribution of the velocities inside above the canopy. And this is what we have to deal with. Just to take a deeper look into this kind of non-ideal nature of the...
May I ask a question on the slide before? So does it say that it's more isotropic at the bottom of the canopy than at the top of the canopy? Because if you have a soft on the top, it means that it's more or less isotropic, no? No?
Yes, I'm sorry, maybe this is a bit confusing. The top picture right here is inside the canopy.
Yes.
And here we have a quite isotropic distribution of the velocity. And then higher above, this is maybe the bottom picture, but it corresponds to this region.
Yes, yes.
Where we have a very strong anisotropy of the velocity.
But it's surprising to find it more or less isotropic at the bottom of the surface, no? It's surprising.
No, so since we have inside of the canopy, the turbulence is kind of dominated by small scale structures. I would say this is not very surprising to see that the flow inside is much more isotropic as compared to outside. So I would kind of attribute a lot of this anisotropy to the existence of these large coherent structures right above the canopy.
I mean, I was expecting both sides to be isotropic, but I'm surprised to see it more or less isotropic in this representation at the bottom of the surface.
Yeah, well, I guess this is really related to the strong turbulence that we have inside. So for example, the turbulence intensity right here, this region, is well above, I don't know, 200%. The fluctuations are much, much, much more stronger than the mean flow. So, yeah.
Okay, cool. Thank you.
Sure. Okay, so just to represent this non-ideal nature of the canopy flow in more detail, we can divide the different trajectories into 4 different groups. And we can do this as follows. So if we have the joint distribution of the velocity fluctuations in the streamwise direction and in the vertical direction, this is kind of how it looks. We can divide the trajectories into these 4 categories. We have Q1, Q2, Q3, and Q4, depending on the quadrant at which the velocity is founded. So for example, these Q1 particles, the particles that belong to this group, have a strong streamwise component of the velocity, plus a strong vertical component of the velocity. But these particles have a low component of the streamwise velocity and lower than average component of the vertical velocity. And if we kind of try to put it in the context of the canopy, then perhaps these particles will move very fast upwards and stay away, try to kind of escape from the canopy. But for example, these particles, these Q4 particles, will be also very fast, but protrude inside of the canopy from the boundary layer that's above it. Right, so this is just a categorization that we can use. And then I would like also to define the following property. I denote it as A, and it's defined as follows. Here is E. E represents the kinetic energy of the particle. From that, we subtract the average kinetic energy of that same particle. Then we square it. Then we take again the average along the trajectory, and we take the square root. So essentially, A is a kind of standard deviation for the fluctuations of kinetic energy felt by a single trajectory during some finite period of time. This can also be represented in this can also be shown, for example, in this graph, where we have two different particles. This kinetic energy of the blue particle is seen right here, and it seems to change quite considerably around its own average value. And this corresponds to a high value of this A parameter. But this orange curve that corresponds to a different particle had quite a low value of this A parameter, and its kinetic energy remained almost constant. And then here in this figure, I just plot the probability distribution function for this parameter A across many different trajectories that belong to the different groups that we have considered. What we can see is that for particles coming from different groups, they had quite different distributions of this A parameter. So for example, these Q4 and Q1 particles, this is their PDF right here in red and blue. And we see that they had characteristically much higher values of this activity, this A parameter that I sometimes call an activity parameter. Whereas the particles from the other two groups, for the Q4, for the Q2 and for the Q3 groups, for the yellow and for the green curves, their PDFs show that they had characteristically much lower values for this A parameter. Now, since this parameter A is associated with fluctuations of the kinetic energy, or changes of the kinetic energy, we see that conditioning on the direction, right, of where the particle is moving, we have an asymmetry of this energy input into the trajectories. So we have a symmetry breaking with respect to the particle's motion. This, at least to me, suggests that we have a dependence of this energy input into the turbulence due to the canopy drag. How can we see that this is related to the drag? Because these Q4 and Q1 groups are basically faster trajectories. So they encounter the canopy elements at a higher velocity, which results in a higher drag, and then leads to higher values of the fluctuations of their kinetic energy. And the opposite occurs for the two other groups of particles which were slower. So essentially, this is a very non-ideal kind of picture for our turbulent phenomenology to exist in. However, I suggest that we try and take perhaps a closer look into that. So to look closer or deeper into the smaller scales of the turbulence, we can consider what's called the Lagrangian velocity difference, or the velocity increments, as we call. So basically, we have a Lagrangian trajectory seen right here. It has a velocity at time t, and it has a velocity at time t plus tau. And then we just subtract this velocity at this time minus the velocity at this time, and this is called the Lagrangian velocity difference. The Lagrangian velocity difference is an important property to study because it allows us to look on the turbulence dynamics at different scales, right? So if we change tau, we change our scale of observation, which allows us to kind of study statistics of turbulence at different scales. In addition to that, statistical moments of these velocity increments are called structure functions, defined right here. And these are very fundamental objects that people work in turbulence theory. So basically, we just take this velocity increment, only one component of the velocity increment, and we plot the PDF for different trajectories and for different values of time, different values of tau. So for example, this blue data, this blue curve right here corresponds to very small values of the time, to tau equals 0.3 times the Kolmogorov timescale times the dissipation timescale. But on the other hand, this purple data corresponds to velocity increments at much later times. So so here we have 11 dissipation timescales. And the striking feature of this picture is that as we change the time, as we change the scale of our observation, the PDF of the statistics change quite dramatically. So for example, if this blue data has a very wide tails, meaning that we have a high probability for extreme events to occur, then this property or these wide tails relax very strongly as we increase the time of our observation. And this gray curve, just a comparison to show how a Gaussian, a normal distribution looks like. So yeah, as I said, the PDFs clearly change their shape with the time scale. This can also be studied quantitatively using the flatness factor. So this is just the fourth moment of the velocity increment divided by the squared second moment of the velocity increment. And as we can see, it changes again very strongly with the time scale. So it is rather low at large time scales, but it is much, much, much higher for very small time lags. And this corresponds to the Gaussian value of 3. And so again, this shows that extreme events are more frequent. Yes.
So,
yes, Laura?
What is the order of the ratio of the Kolmogorov timescale over the integral timescale of the flow? Is it 10 or 12 or something?
So for our flow, for the canopy, so first of all, it changes as a function of height. So if we look high above, it's one value. If we look down inside, it's a different value. But roughly speaking, it's around, I think, 8 Kolmogorov timescales. So yeah, the integral timescale for our flow with relative to the dissipation timescale is very low in our canopy flow, although the Reynolds number is high.
Okay.
Yeah.
Thank you.
We addressed this question in our paper. We can discuss about this later. As I said, basically this figure showing the flatness factor as a function of time shows that as the time scale decreases, we have a higher probability for extreme events because the flatness factor increases very strongly with the time scale. And this is essentially a clear deviation from the self-similar picture that we have shown for the fundamental cascade of turbulence. And it's very important to realize that we are not the first one who saw this, this observation for Lagrangian statistics. So for example, here we have data from 4 different papers. So this is the data, experimental data by Mordant et al. From 2002. This is direct numerical simulation by Benzi and his co-workers from 2010. These are two graphs by Laurent and his co-workers. Here we have an experimental data, and here we have data of simulation, which again shows the same characteristic change of the PDF as a function of time. But the main difference is between this data and the data that we show for the Canopy flow is that these data were taken from almost ideal kind of turbulent flows. So for example, if we have simulations for these two graphs, then the simulations use, they're homogeneous and isotropic by construction. So the forcing is usually maintained all across the volume of the flow homogeneously. And in the experiments, so these two graphs come from typical experiments that people do in laboratory scale experiments. So for example, people take such tanks full of water. They put two rotating disks that rotate in opposite directions. This generates a very strong turbulence inside of this vessel. And then people study the dynamics of turbulence right here, very far away from the disks. And here again, it's common to say that the flow is at least quasi-homogeneous. So the direct effect of the disks right here in the middle is not very strong. So we can say these are quasi-homogeneous flows, whereas our flow is very strongly inhomogeneous and anisotropic. But still we see a very similar picture. So in order to learn more about our Canopy flow, let's look at the models that people have developed in these more ideal cases.
I have a question.
So
excuse me.
In order to tackle...
No. Can you hear me?
Yes, sure.
Okay, it's Nicolas.
Yes, I can hear you.
Yeah, the flow is strongly inhomogeneous
hello.
in space, so it means that all the statistics should depend a lot on the initial positions of the particle. Did you try to condition especially your statistics?
Yes, of course. If we look at different locations of the flow, we see different statistics. Here specifically, for the results that I'm showing right here, we took one small volume of space, and we took only particles that are emitted from this, that are moving inside of this subvolume of space. It was still inside of the Canopy flow, so still it could feel some gradients of, so for example, the particles that they move, they could feel different statistics of the turbulence if the inhomogeneity is very, very strong. So does this answer the question? Okay, I hope so.
Sorry.
Okay.
Yeah, okay, fine.
So
fine.
relying on the sure, thank you. So let's go back. Trying to study from what people have seen in these quasi-homogeneous or more ideal kind of turbulent flows. We have to, following their track, we need to change our frame of mind. So instead of a self-similar cascade, we'll now try to transition into what's called a multifractal picture of turbulence. So changing the picture looks conceptually in our mind something like that. So instead of the turbulent eddies filling the volume of fluid homogeneously across all the steps of the cascade, now we imagine that some of these eddies of the turbulent vortices are lost along the cascade, and that this process occurs randomly, right? And this gives us kind of an intermittent picture of activity at the smaller scales. And still we imagine that across this cascade of energy, we still have the same level of energy at the input level that is being dissipated due to friction at the bottom level, meaning that energy is not being leaked out throughout the cascade. So mathematically, without going into the details of this multifractal model, the velocity increments are described as being comprised of two contributions. So we first have a random contribution denoted as B, which is a random function of the separation of a scale that we are looking at, times another contribution that comes from the fluctuations of velocity increments at the largest scales, right here. And then essentially statistics of B, of the random function B, determine the small scale structure of the flow. So again, without going into the detail, this essentially determines the distribution of scaling exponents that we have for the flow. So if in the self-similar picture, we had a one fixed and constant scaling exponent, here the scaling exponents change, they're random variables. And the question is, can this extended picture of the turbulence cascade work for our canopy flow data? And the answer is yes, it can work for our data. So basically taking the same function B as Laura Chevalier took in their data to represent the ENS data in their experiment from homogeneous flows. So taking the same function as they used in ideal flows, and then just fitting two free parameters, we're able to obtain a very, very good agreement between our experimental canopy flow data and the multifractal picture. So the model is shown right here in black lines that underline the data. And we can see that we have a very good agreement with this transition of the PDFs as we change the time scale. And the same thing is observed naturally also for the flatness factor. So again, this black line shows the transition of the flatness factor, and it is really quite remarkably agrees with our canopy flow experimental data. Another question that we can try and ask is, do we have a similar kind of vortex filamentation of the small scale structure of the canopy flow as people have seen in the ideal flows?
Excuse me, Han, about
Yes?
the last slide on the fits. How do the parameters compare? No, the previous one, yes. How do the parameters compare with homogeneous turbulence?
So they differed. I don't remember the exact numbers, but I can look that up in the paper that we wrote right here. I don't remember the exact values, but they were different from what the Laurent et al. Obtained for their data.
Okay.
So yeah, we needed different parameters, but essentially the same structure of the function was the same. This is the important issue.
Okay, thank you.
Sure. So about the small scale structure of the flow, do we obtain such a vortex filamentation kind of structure of the small scale structure of the flow? So to try and answer that, we can look at the correlation functions of the velocity increments with very small time steps. So if we, for example, imagine that our trajectories are moving in some kind of spiral motion around the cores of vortex filaments, then their velocity components would become decorrelated at the rate at which they kind of circle these vortex filaments. However, the magnitude of their velocity would stay the same, roughly. And this is exactly what is shown in this picture. So these blue data, blue data points show the autocorrelation function for the velocity increments of the velocity components. And we can see that they decrease very, very fast by the value of 2 dissipation time scales. It reaches almost 0, and then it becomes almost anti-correlated for a significant amount of time. However, the magnitude of the velocity increment remains correlated for a significant amount of time, actually longer than our entire recording. And this again, indeed is consistent with this kind of vortex trapping picture that exists in ideal turbulent cases, only that this is taken from a canopy flow. And for example, I'm showing here this, I don't know, spiraling trajectory that I found using some looking into the data that kind of is reminiscent of this vortex filamentation picture. So basically, I showed you here two examples in which theory that came from the idealized kind of pictures of turbulence, albeit adjusted for intermittency, we have a great agreement between what we see in the canopy flows and what people saw in the idealized or ideal kind of homogeneous or quasi-homogeneous flows. I could have showed you also that we have almost the same scaling laws for the structure functions. I don't have a lot of time for that. I could have also shown you that the dispersion, at least the scaling for the dispersion, is also the same as we would have expected in the ideal cases for our canopy flows. So essentially, our results, concerning the question that I posed at the beginning, our results suggest that yes, the cascade adjusted for intermittency can exist in the highly inhomogeneous and anisotropic canopy flows. And this actually extends this, this very nice, very beautiful paper that was published in 2008 that talked about the universal intermittency properties of Lagrangian trajectories in highly turbulent flows, only that they looked only on idealized flows, whereas we are looking on a very non-ideal situation of the turbulence. In order to tell you why, so it's quite a long answer. So the short version of this answer is that this happens due to the very high turbulence intensity that we have in our flow, that essentially leads to a kind of separation of scales. So the inhomogeneity is felt on a very long time scale, whereas what we see here, the turbulence cascade and this intermittency picture existed on only on very small time scales, but still relevant to have at least a partial inertial range of the turbulent flow. So to conclude, we wanted to have a more physical understanding of what goes on inside canopy flows in order to be able to model dispersion in a better way. In order to answer this question, we did an experiment inside of a wind tunnel. We used 3D PTV in order to obtain an extensive Lagrangian data set and to analyze these canopy flow statistics. And the take-home message from this talk is that fundamental turbulence phenomenology is very relevant, even at very strongly inhomogeneous and non-ideal flows, provided that we have sufficiently small scales at which we are looking at, and that we are considering flows with sufficiently strong turbulence. With that, I would like to thank the organizers who invited me, Laura Chevalier and Elsa Baya. I would like to thank Alex, Yardena, and Eyal, without whom this entire research would not have been possible. I want to thank my friends at Tel Aviv University, at the IIBR, and at the Weizmann Institute, where I'm currently at. I want to thank the PASI Foundation for funding this research. And of course, thank you very, very much for listening. That's it.
Thanks a lot, Ron, for this very pedagogical talk. Feel free to just ask question directly, open your microphone.
So I have a question, well, several questions actually. Thank you for your presentation. That was a very nice experiment actually. We did experiments Lagrangians of the Lagrangian properties in a turbulent channel flow with smooth walls. And we saw that the PDF of the acceleration changed quite a bit when across the boundary layer. In particular, there is at some position strong skewness, actually. Did you investigate a little bit more when you go to the boundary of the canopy, let's say, how the PDF of the increment changed?
Yes, so first of all, I'm aware of this work. I've been looking at it quite intensively. Yes, we did look into the accelerations. I did not present this data here. Actually, we did not, I do not remember that we saw a significant skewness of the distribution of the accelerations, different locations of the flow. The distribution was indeed very flat, as characteristics of well-known phenomena that occurs in turbulence. We have very fat tails of the distribution. The thing that was interesting is that, so for example, if we looked at the scaling of the acceleration using the Kolmogorov similarity theory, it can be related to the large scale to the integral scale of the flow. I don't remember exactly the formula, but there's a formula for the variance of the acceleration, which can be predicted given the dissipation, the dissipation of the energy and the integral scale of the flow. And then we saw that moving across this boundary, we see a very sharp change for this specific property. So inside of the canopy itself, we saw a clear scaling that agrees with Kolmogorov. Above the canopy, we saw a very nice scaling that kind of agrees with the Kolmogorov picture, but right at the at this interface between the two regions, we saw a clear deviation that marked like a transition from one type of turbulence into a different type of turbulent flow. I would suggest this appeared in our scientific report paper, which I can send you afterwards.
Okay, thank you. I have a second question, maybe.
Sure.
If you want to look to investigate the dispersion, it's more a matter of long time dispersion. So did you look at long trajectories and what happened at long time scales?
Yeah, so for actually our experiment, due to technical difficulties of measuring trajectories inside of this wind tunnel in between the canopy roughness obstacles, our trajectories are rather limited to relatively short distances. So they moved roughly in between two consecutive rows of elements. And in this region, we saw quite a great agreement actually with the Taylor theory for dispersion. So initially it is ballistic and then it goes to a diffusive regime of scaling for the dispersion. If we had longer times, it would be amazing to see how this dispersion is affected at a longer time scale, but unfortunately it was not available for the current experiment that we have.
Yeah, I imagine it's a real challenge, yeah, sure.
Yeah. Yeah.
So I didn't say it, Nicolas, but Ron is supposed to go to Zurich next year with Olsner.
Yes.
So maybe that would be a good occasion for you to invite him in Grenoble and to visit the experiments and talk about physics. Nicolas?
Sure.
Great.
I would be very happy to come, of course.
That's a very nice talk, Ron. Thank you.
Thanks. Thank you very much.
Yeah, it's an amazing experiment, actually.
Thank you. It was, yeah.
I have a question about your introduction. You say that there are not so many experiments with the Lagrangian approach. Could you actually use, I don't know, chemical accident or nuclear accident to follow the dispersion of particles in the air, and then it's like a
we are not wishing for a nuclear accident in the world. Let's be clear.
Maybe not nuclear accident, but if there is like a large fire or some chemical industry, like in Lebanon, the explosion, or I don't know.
Yeah, so for example, when the Fukushima disaster happened, I know that a lot of people tried to measure how much time it will take for the chemical cloud, for the not chemical, for the hazardous clouds to get from Japan to Europe, etc. And there was, of course, this famous accident of the ship that broke down in the middle of the Atlantic with a big shipment of rubber ducks that ended up being dispersed across the entire oceans of Earth. So people were kind of reporting where these rubber duckies found across the shores. So this is of course very interesting, but I think so when we are tracing the concentration field, of course it's very important, and essentially this is our eventual goal to actually model this dispersion of concentration. But we really want to be able to say what is the history of each individual particle in the turbulent flow, because we know that I mean, this is the recent experiments and all of the simulations that have been performed in the last 20 years. They have revealed that where the Lagrangian traces come from and the entire route that they make until they reach our point of observation is very important. And then, so essentially, if the concentration of these blobs of fluid changes as a function of time, I'm not sure that we will actually be able to kind of pinpoint the motion of these concentration clouds, because essentially there is diffusion and there are changes that occur to this concentration of the traces.
Yeah, you would maybe need to image the very first moment of after an explosion or something. Then
yeah,
you don't want
like
to trigger the boom. Then.
Yeah. Thanks for the question.
Other questions?
I have one. Thank you for the talk, Ron. It was very nice. Why did you choose the small plate, big plate arrangement for the canopy? Is that supposed to match a city or a forest or something?
Yeah, so obviously forests don't really look like flat plates. But in order to perform this experiment, we had to have a lot of optical access, you know, to actually see. So if maybe I will show this, oops. Maybe I will show the image of the cameras outside, and it will be clear to understand. Yeah, okay. So if the cameras were positioned outside of the wind tunnel, then in order to see what is going on right here in between these canopy obstacles, we need to have a clear optical path in order to see them. And this has eventually led to the choice of having these flat plates. And then we knew that we wanted to have a high turbulent intensity because this would be beneficial for our for the PTV experiment as well, because this would mean that particles spend more time essentially in our region of interest. And so we added also these bottom lower flat plates in order to actually try and increase the turbulence intensity, try to increase the frontal density of this entire canopy layer. Of course, it will be very interesting to see what happens with these bottom plates, without these bottom plates, by changing their appearance, etc., etc. But this is not my job anymore. It would be the job of the next experimentalist who goes into the wind tunnel. I mean, maybe it would be me in a few years.
Thank you. And one last question. Also, where do you measure exactly in the canopy? I mean, like in the middle of the canopy at the end?
So we did a series of measurements. We started from this region, right above the bottom plate, and then we slowly increased the height, increasing up until roughly this region. So we have statistics from this entire region.
No, but I mean in the stream direction.
Come again?
Like in the streamwise direction, like from.
So we have a 14-meter long test section of the wind tunnel, and we were measuring in the last 2 meters of the wind tunnel. So we have roughly 12 meters of this canopy construction ahead. Yes, yeah. And again, this is kind of connected to Elsa's question from before. We want to have a real kind of model of a boundary layer incoming above these roughness obstacles. So we need to have a very long wind tunnel with a long construction of this canopy flow.
Yeah,
this is why we did it.
Thank you.
Of course, thank you.
Last chance for questions. I mean, not last, but for this seminar.
Yeah.
Okay, then I think we can thank Ron again for this talk. And okay, I hope we will see you if you visit Grenoble or Lyon, that you'll come to the lab.
I will be more than happy to come and visit.